Hello my dear students, myself Madhu CA from the Department of Physics. Hope you are safe and secure at home and doing well. Your physics classes had already been started and it's taken by Dr. Binoy Anand sir. I am also handling a unit in your physics paper. So the first unit, unit 1, that is elasticity, will be handling by me. And today we are going to start this module. So this is my first class. Here in this class, I am not going to take any new topics in elasticity, but I am taking what you had already learned in your plus 2 classes. So let's start our class. So our module name, unit 1 name is elasticity. You know that Newton's laws of motion are the fundamental laws of mechanics. Mechanics means study of moving particles, isn't it? So the fundamental laws of mechanics are Newton's laws of motion. Using this Newton's laws of motion, we can explain all the mechanical property of matter. And you know that Newton's laws of motion contains 3 laws. And the first law is related with inertia, which is the property of material bodies. Inertia that gives you mass to the particles. So it is a property of all the material bodies to have inertia. Now Newton's second law. Newton's second law relates the force and momentum. So the what effect an applied force produces to the state of a motion of a body is described by the second law. Using second law, you can define what is an applied force on a particular body and its related physical quantities. And the third law, you know that the third law states that to every action there is an equal and opposite reaction. This law is related with our topic elasticity. And what is meant by elasticity? Elasticity is the property by virtue of which the material bodies are capable of exerting reaction forces. So a force is applied on the body and now the body has a property to react to the applied force. So that is the reaction forces. So if the material is capable, if the body is capable of exerting reaction forces, that property is called elasticity. So we are applying a force on a body, so that is applied force, and the body responds to that force by a reaction force. So according to third law, to every action there is an equal and opposite reaction. So the third law associates elasticity with it. So all material bodies undergo deformation when subjected to suitable external forces. So when we apply force on a body, there will be some change on that body. That change is called deformation here. So all the material bodies undergo deformation when it is subjected to suitable external forces. For example, when a rubber ball is pressed, its shape is changed, isn't it? It is deformed. And what happens when the deforming force is withdrawn? First you apply force on that rubber ball so that it got pressed, so that its shape is compressed. And when you remove this applied force, what happens? It regains its shape, isn't it? Now the second example is a steel wire. When a steel wire is suspended at one end and it is loaded with a weight at the other end, what happens to the steel wire? The steel wire gets elongated. And when this load is removed, it retains or regains its original length. So that are the simple examples which help you to identify how an applied force is given and how it is removed, so that the material body regains its shape after the removal of deforming force. So that is the ability of that body to regain its original size and shape when the deforming force is removed. And this property is called elasticity. The ability of a body to regain its original size and shape when the deforming force is removed is known as elasticity. And what do you mean by a perfectly elastic body? So the body which completely regains its original size and shape after the removal of the deforming force, we can say that it is perfectly elastic. And if the body is unable to retain its original state, it will be perfectly plastic. That means a body which retains its deformed condition and shows no tendency to regain its original state. Such bodies are called as perfectly plastic. So when in the case of a plastic body, when we apply force, its size and shape is deformed or changed, and after the removal of the applied force, it will be seen as such. There is no change in the body, or it will not have the tendency to go back to its original state. So such bodies are called perfectly plastic, and there is no such material which is perfectly elastic or perfectly plastic. But we can give an approximate example as quartz fiber for perfectly elastic body and putty for perfectly plastic. So there is no material which is perfectly elastic or perfectly plastic. In the case of solids, the location of molecules or atoms is nearly fixed. You know that there are immobile molecules in solid. Immobile molecules means you had studied the structure of solid as closely packed structure, isn't it? So the molecules are not able to move inside the solid, so that it gives the solid a definite shape and rigidity. And this rigidity is the cause of elastic behavior in solids. So what happens when we apply a force on a body? It's very important. When an external force acts on a body, the particles in the body undergo relative displacement. And inside the body, there will be an equal and opposite reaction force which opposes the deformation of the body. See, we are applying an force on the body. So the body will get deformed, isn't it? So in order to oppose this deformation, there is an equal and opposite reaction force that is developed inside the body. And it opposes the deformation and it helps the body to come or to go back to its initial state, or it will help it to retain its original shape and size. So the body will come to an equilibrium when this external force as well as the internal reaction force are equal. So when the balance will be there, when there will be balance, when this external applied force is equal to the internal reaction force. Now what happens when the external force is removed? There is internal reaction force inside the body, isn't it? So due to this internal reaction force, the body tends to regain its original condition. So that is what's going on inside a body when we apply an external force on that body. I repeat, when an external force acts on a body, the particles in the body undergo relative displacements. There will be an equal and opposite reaction force which opposes the deformation of the body. And the body will come to an equilibrium when external force and internal reaction force are equal. As the external force is removed, because of the internal reaction force, the body tends to regain its original condition. So this graph is familiar to you. It's a load extension graph or load extension curve, where we suppose a metal wire such as a copper wire or steel wire whose one end is rigidly fixed to a support, and at the other free end a weight is suspended. So what happens when a weight is suspended at the free end of the metal wire? The wire undergoes elongation. And we have plotted a graph between the applied force and the elongation produced, that is the extension. So along x-axis we have extension or elongation produced, and along y-axis we have the applied force. Here you can see the graph that up to the point A we got a straight line. That means the graph is linear in the region OA. That means the extension is proportional to the applied force. And the condition is that for small applied forces. So we are increasing the value from the origin, from the 0, isn't it? So for small applied forces, the extension or elongation produced is proportional to the applied force. That means along this region, the material behaves as an elastic material. That means whenever we remove this applied force, the body will retain or regain its original size as well as shape. So that is the linear portion of the graph. That is, for small applied forces, the extension is proportional to the applied force represented by the portion OA in the graph. Now A is the point called a limiting point, or we can say that it is known as the elastic limit. So what is meant by elastic limit of a material? You know that up to A, the extension is proportional to the applied force. So how we can define the elastic limit of a material? Elastic limit of a material is the limit within which the applied force and the extension are proportional to each other. Up to which the extension or elongation produced is proportional to the applied force. That point is known as elastic point. And beyond A, what happens beyond A? Beyond A, the body behaves like a plastic body. That means if the applied force is removed, the body does not come back to its original size or shape, but it continues to remain deformed. After the limiting point A or the elastic limit A. So before A, the particle or the material behaves like a elastic body, and after A, beyond A, it behaves like a plastic body. So the same body behaves like an elastic body for smaller applied forces and like a plastic body for larger applied forces. So that is a load extension curve. You know the term stress, isn't it? So when a deforming force is applied to a body, it reacts to the applied force by developing an internal reaction force. And this reaction force is equal in magnitude but opposite in direction to the applied force. So you know what happens to a body when a force is applied. So when an external force is applied on a body, inside a body there develops an internal reaction force which is equal in magnitude but opposite in direction to the applied force, which helps the body to retain its shape after the deforming force is removed. So this internal reaction force per unit area is called stress. Internal reaction force per unit area, and we know that this internal reaction force is equal to the magnitude of the applied force, isn't it? So we can also define stress as the magnitude of the applied force per unit area of the body. Why we are taking magnitude? We know that internal reaction force is equal but opposite to the applied force. So we are just taking the magnitude in order to get the value only. So the stress is also defined as the magnitude of the applied force per unit area of the body. And we know that this stress is internal reaction force per unit area. We had defined it as internal reaction force per unit area. So that the direction of stress will be, we know that internal reaction force also always opposes the applied force. So the direction of stress is opposite to the applied force. So how you can write the equation for stress? It is the reaction force by area. Now its SI unit is force is Newton and area is meter square. So it is Newton per meter square. And you can derive the dimensional formula as m L raised to minus 1 T raised to minus 2. You can do it as a homework for you, how to derive the dimensional formula for stress. Now, whenever we apply an external force on the body can have several deformations or several changes. So, depending upon the nature of the deformation produced by the stress is categorized into three. So, depending upon the nature of deformation produced by the stress, we can classify stress into linear stress, volume stress, shearing stress. If the stress produces an increase in the length of the body, then that stress is known as longitudinal or linear stress. If it produces a change in the volume of the body, then it is known as volume stress or normal stress. And if the stress is tangential to the surface of the body, it produces some change in the shape of the body. Then such stress is known as tangential or shearing stress. So three types of stress. If the stress produces an increase in length, it is longitudinal or linear. If it changes the volume of the body, it is called volume stress or normal stress. If it is tangential to the surface of the body so that it changes the shape of a body, then it is called tangential or shearing stress. So now we know about the stress. So obviously the next topic will be strain. Now what is strain? Strain is the ratio of change in dimension to the original dimension. So that's the equation, and you know that it has no units, no dimensional formula, etc. Now we are going to study about the different types of strain. Since there are three types of stresses, there are three types of strains also. And strain is a dimensionless or unitless quantity. So first stress we had discussed is longitudinal or linear stress. So the corresponding strain will be longitudinal or linear strain. So here we can consider a wire which is fixed at the upper end and is suspended with a weight at the free end. So here you can see that the wire is having a length capital L. So what happens when a weight is suspended at the free end? Its length is elongated, isn't it? So that the change in length is given by small l. So small l be the increase in length. So how you can calculate the linear strain or longitudinal strain? It is change in length by original length, and you know that the increase in length is small l. So small l divided by capital L gives you the linear strain. Now next is volume strain. Here you can see a cuboid where the deforming force is acting normal to the surface of the body. See, there are several surfaces and this deforming forces acting normal to the surface of the body. So it produces a change in the volume of the body. Let capital V be the initial or original volume, and let a small v be the change in volume when the deforming forces applied. So how you can write a volume strain? Volume strain is change in volume by original volume. So that is small v by capital V. Now the last type of strain is a shearing strain. Here we had considered a cubical body and its lower face is fixed and the deforming force is applied tangential to its upper face, so that only the upper face goes a displacement. You can see the cuboid or cubical shape with the sides A, B, C and D, and the deforming force is applied on the upper surface. So D is changed to D dash and C is changed to C dash, so that the change in displacement is small l, and the length AD is given as capital L. And this upper face undergo a displacement, or we can say that the body is sheared through an angle theta. The deforming force is applied tangential to the upper face, so that it undergoes a displacement, or the body is changed or sheared through an angle theta. The small angle denoted there is theta, and the angle theta measured in radians is called the shearing strain. So what is angle of shear or shearing strain? Shearing strain is also known as angle of shear. So how can we define angle of shear? Angle of shear is the angle through which a line originally perpendicular to the fixed face is turned by the action of a tangential stress. You know that AD is equal to capital L is the line which is perpendicular to the fixed face AB, isn't it? Now what happens when this tangential stress is applied? When tangential stress is applied, D changes to D dash. So that is how we define angle of shear. Angle of shear is the angle through which a line originally perpendicular to the fixed face is turned by the action of the tangential stress. And from this, the angle tan theta is opposite side by adjacent side. So tan theta is equal to small l by capital L, and we know that this theta will be very small. We cannot see the angle changed. For convenience, we are giving it in the figure as angle theta, but the theta will be very small. So when theta is very small, we can approximate tan theta as a theta itself. So theta is the angle of angle of shear, or it is known as the shearing strain. So theta is equal to small l by capital L. So that's about the shearing strain. So let's have a look on what we had covered. We had defined what is elasticity, and we had seen the load extension curve with the definition of elastic limit, and we had covered stress, different type of stresses, and also the corresponding strains. I hope there is no new topics for you. This is what you had already learned in your previous plus 2 classes. So I think this class will be helpful in remembering all those classes, and make a note of this class This is also included in our first module. For any doubts, you can make a chat in our WhatsApp group. Thank you.